years ago, and in the huge tide of communication that's always washing back and forth across my computer, at first I didn't pay a whole lot of attention, I must confess. But he is worth paying attention to, and I found that out after reviewing some of his work. So Ron is going to give us some good theoretical background. He's worked as an engineer for many years. He's worked for companies including a 200 megawatt power plant. Oh, 2,000 megawatt. I wrote that down wrong. I'm sorry. He's also worked as an engineer at Collins Radio Company, IBM, and a steel plant. Currently, he works as a builder of antennas in a private company. He told me he never felt satisfied with explanations of how radio propagation works. And this led him to a search, and now we're going to hear Ron Nott with the results of that search.
Thank you, Mike, very much. At previous conferences, some of you may have heard some of Mike's witticisms. He used to, and I talked to him this morning and he said they're all gone, little jokes and witticisms and so forth. And I suggested to him one last year that he said wasn't appropriate, but I'll do it anyway. It's just a quotation from old Will Rogers. He was from Oklahoma, as is the gentleman right here, and I. So he and I can do this. Will Rogers said way back there during the 1930s in the era of the Dust Bowl, he said, if the Okies, or when the Okies moved to California, it raised the IQ of both states. Now, it's possible that if the descendants of the Okies would move back now, it might have the same effect. I don't know. But at any rate, we've heard some extremely good talks here. And one of the things is we need to differentiate between space and particles. They're entirely different. And they both have their place and they work together. But my research has been in the area of space. As members of TeslaTech, we're all interested in every form and source of energy, what it is, how it works, and where it comes from. These were the overwhelming interests of our namesake, Nikola Tesla. There's the gizmo. He had greater insight on all of these energy things than anyone of his day, and he described this energy as cosmic energy, which is everywhere. And when I say everywhere, we'll plow into that and explain it. But the space that I'm looking into has no particles. If you're looking for hydrogen energy and things like that, it doesn't fit here. Today, our society is highly dependent on fossil fuel thermal energy. Our power plants and our vehicles, our business and our homes are almost totally powered by the combustion of fossil fuels. For the time being, these fuels are very abundant, and the technologies are relatively simple, and some people, and this is important, are reaping huge profits from them. And for all these reasons, these will not go away soon. However, there's not an infinite supply of these fuels, and the cost of extracting them will also increase in time. There are serious problems with them, the most well-known being pollution and global warming. Both adversely affect our biosphere, where we live and breathe. So the question is what else is there? While our politicians and industries are now dominated by fossil fuel technology, we know that experimenters over the last century have invented and developed machines that seem to have net power gain. That is, once they're started, using conventional energy, they output more energy than they take in. The big question is, where is this energy coming from? For more than a century, the term fabric of space has been mentioned frequently, but seldom does anyone define it. Let's look at Webster's definition of it. It says, a cloth made by weaving, knitting, or felting fibers, the texture of a cloth or material, framework, structure, the method of construction. What we see here is it's organized. Our Creator put it together in a good form that is useful and worthwhile. The question is how does this apply to space itself? While people had been tinkering with magnets for many years, Michael Faraday recognized that the magnetic force is within the space surrounding the magnet. The force is also within the space inside the magnet, and we'll find out that the magnet is mostly space. Classic iron filings on a sheet of paper will demonstrate this field, this magnetic field, but the force around it is always there even if there's no iron filings. Without the filings, it is invisible. At first, Faraday described it by lines of force, and he drew these pictures, which are still effective nowadays. But later on, James Clerk Maxwell defined it as a field surrounding the magnet. So all of us, everyone, Murray King spoke of fields and all this stuff, and so we all live in fields all the time. If we run some current through a wire, let's say DC current, there will be a field around the wire. This is an illustration which is not particularly good, but it does show that extending outward from the wire, there's an electric field. One thing that's interesting is Hans Christian Ørsted was the person who is given credit for first observing the magnetic field in the space surrounding the wire, carrying an electrical current. And there's an interesting story. He was a teacher, and he had a class of students. And one of the things is that he and others had assumed that the current flow and the magnetic field would be in the same plane. So what they would do, they would cause current to flow through a wire with a battery, and they would hold a compass up alongside it, and they'd always assumed that they would be parallel. Well, he had one student that wasn't quite as bright as the rest, and he went up to the wire one day and he turned the magnet sideways or crossways, and the needle deflected. Well, this shows that you don't want to ever assume anything. You want to find out. And when they had assumed that the field and the magnetic field and the current would be in the same plane, they were wrong. They're perpendicular to each other. When all of the old experimenters began to study capacitors, they learned that an electric field exists in the space between the plates of the capacitor. And I always emphasize space in this because that's what we're talking about. In many cases, this space is filled with a solid dielectric, but even this material, the dielectric, is mostly space. The strength of the field varies depending on the material between the plates. From one extreme to another is a vacuum to a tantalum compound. You know, if you know about tantalum capacitors, they can have extremely high dielectric constant. So let's just look at a definition of space. And this is a Webster's dictionary definition, which is not really good at all for our purposes. The unlimited three-dimensional realm in which all material objects are located and in which all events occur. It's extremely it's right, but it's, you know, for our purposes, it's quite limited. First, we need to consider what's in the space inside this room. There is radiation of all kinds. If we were to bring any kind of a little radio in here and turn it on, we would irritate all the other listeners because there are probably dozens of radio signals in here from the local broadcast stations. And if we brought in a portable TV, we could get a lot of channels. If we brought in a shortwave receiver, VHF, UHF receivers, and of course these cell phones, you could hear thousands of teenage conversations. And it's all here, all at the same time. We just don't have a device called a receiver tuned in to detect it. But the important thing, this space is full of electromagnetic energy. They come from all different directions and many different strengths. So this room is rich with RF energy, and don't forget the cell phones. The electromagnetic spectrum is loaded, but apparently unlimited. To illustrate space inside the materials, this is a crude description, and this is not my own, but I think it's appropriate. Let's say, let's think about an atom, and we assume that the nucleus, which is the protons, neutrons, and other atomic particles that are in a nucleus, has been enlarged to the size of a housefly. If we then place the fly at the center of the 50-yard line of the Super Bowl, or we place it there. Now, if you look up at the roof of the, oh, playing with it. Okay. All right. The roof, if we look way up there, that represents the first orbital shell of the atom. When the first layer in which electrons are whirling around the nucleus. The other shells are way above the roof. Even though the atom has been vastly enlarged, the electrons are still too small to be seen by the human eye. It would take something like an extremely good electron microscope to see it. The point of all this is that every atom is by far mostly empty space. Now, that's a mistake, because when I said empty space, that term is used by a lot of people a lot of times, but it's never really empty, except in one event that I'll talk about right at the end. This is a commonly used term, and we'll try to explain that there's no truly empty space. There's always something there. It's never really empty. And, oops, how does this, oh, wrong one. Okay. I've got here a cast iron ball. It looks like an old cannonball. For those of you who have been around a power plant, it's a pulverizer ball. It's solid cast iron, weighs about 4.5 pounds, not quite 3 inches. And when I drop it on the table, it makes a big thump. And I don't want to drop it on my toe because it would really hurt. But if we could somehow remove all of the space, the interatomic space, from this ball of iron, it would become so small that it would be invisible to the human eye. That's how much space there is inside it. Even to the point where, since my hand is mostly empty space, it could just go right through my hand, through the table, through the floor, and down into the earth in all of this space that it's going to travel into. Bear in mind, it would still be 4.5 pounds of weight or mass as you to choose. The proper term would be 4.5 pounds of mass. So it'd still weigh that, even though it was an invisible tiny little clump. If it fell on my toe in this condition through my shoe, it probably wouldn't hurt. It would probably just go right on through. And why I say probably, I don't know. If I hit a nerve or something like that, it might hurt a little bit. And assuming the thing is electric, that ball would be electrically neutral, it could fall hundreds of miles toward the center of the earth until it met material so dense that it would stall, or until it reached the center of gravity of the earth. As solid as it appears, our earth is just a big puffball. It's by far mostly empty space, the subject of this discussion. For decades, our scientists have been concentrating on particles. If you want to be a hero scientist, you discover some tiny, tiny particle that no one ever found before, and you'll become famous. So space itself has been kind of neglected. And we know some old properties of space, and that's what I'll review today. Because if we're extracting energy from space by whatever means, as Moray showed earlier, we need to understand the space where it's coming from. For an illustration, this is to show how that there isn't any really empty space. This is the spiral nebula Andromeda. If you go on the internet, it says it's somewhere between 2 and 3 million light years away, which they vary because nobody agrees on exactly how far it is. But if we could go halfway between our galaxy and Andromeda, would this not be considered empty space? And the answer is no. There are very few particles. The temperature is very cold. It's just a few degrees above absolute zero, but it's not. There has to be something out here and whatever it is, it allows the propagation of light and radio waves from Andromeda to reach our telescopes here on Earth. Whether it's the fabric of space or the ether, something has to be here, or photons will not propagate through this space. While we're out here, halfway between our galaxy and Andromeda, we may be billions of miles away from any solid mass or matter, but there are two properties that are the same two properties found throughout our Earth and our universe. Those two properties are my main subject. They're the same properties that allow an energy field to occupy the space surrounding a magnet and an energy field to occupy the space between the plates of a capacitor. And they're also the properties that are found in the space inside atoms and molecules. Finally, they're the two properties that carry the light from Andromeda to Earth. Alone, one of the properties supports the static magnetic field around a magnet. The other property supports the static DC electric field within a capacitor. In this context, what does support mean? Simply that each property has the capacity to store energy, one magnetic and the other electrical. And recall, we're talking about static storage and not dynamic. The more concentrated each one is, the greater is its capacity to store energy. We'll explain this concentration. What it amounts to is these properties are elastic. They can change. It's kind of like you can compress them or you can expand them or stretch them. Now, the two properties working together, since we know they can store magnetic field and electric field, by working together, these properties support and convey the dynamic propagation of all light, radio waves, and other electromagnetic radiation at the velocity of light. They reinforce one another to allow electromagnetic energy to propagate in leapfrog fashion through the space, inner and outer. Now, the magnetic property is known as permeability, and its value is measured in henries per meter, the units of inductance. Those of you who have worked with electricity and electronics, you recognize that term henries. That was a term named after Joseph Henry, the guy that was the head of the Smithsonian Institution during the 19th century. And the electrical property is known as the farad, which is, of course, named after Michael Faraday. I beg your pardon, it's known as the permittivity, which is measured in farads. And the units of capacitance. Every electronic device has capacitors in it. Radios, TVs, computers, they're here on Earth in the billions. There are references for these things that they've come up with, where it says 8.85 picofarads per meter or 1,260 nanohenries per meter. Those are values in vacuum or in outer space. When they're close into something, such as iron or other materials, these values will change. And so what they've done, they call this value and this value a value of 1. In other words, epsilon, to define the values in a vacuum, it's called epsilon sub naught or mu sub naught, and those are given the value of 1, or unity. And bear in mind, the 8.85 picofarads per meter This is Coulomb's method of doing these things. One of the questions is, do they form the fabric of space? There's James Clerk Maxwell, of the famous Maxwell's equations, and he seemed to think so. He said that the electromagnetic energy, and this was, I didn't get the exact quote, but he said something like, electromagnetic energy, and we're talking about photons, may propagate in a series of jumps. First a magnetic jump, then an electrical jump, and repeating over and over, magnetic, electrical. In other words, it's not just, a photon is not like just a bullet traveling through empty space, because there is no empty space. These properties that we discussed are how it is conveyed. So in the end, what's the main function of these two properties? And in two simple words is energy storage. One can store static, either one by itself can store static or stationary energy, but by working together, they can store dynamic or moving energy. So the question is, how can energy be stored at extremely high speed in the dynamic mode? It's similar, or a good analogy would be like you can put freight in boxcars and it's rolling down the railroad track 60 miles an hour, or humans in a jetliner flying through the air at 60 miles an hour. You're stored there in a dynamic state while you're being conveyed from one place to another. The epsilon, or permittivity, and incidentally that's also in the older electronic stuff called a dielectric constant, has the capacity to store electrical energy, and the mu, or the permeability, stores magnetic energy. As an example, to increase the energy storage capacitor of a capacitor, material with a high relative value of epsilon, and recall I said epsilon sub naught would be the permittivity of a vacuum or space. Whenever it's in material, or you can take a material, for instance in the capacitor, they found that certain tantalum compounds, if you work in electronics you've heard of tantalum capacitors. Well, what they did was simply put tantalum compounds in between those plates, and it can increase the value of capacitance several hundred times. In the case of the magnetic storage, every transformer, the iron in a transformer increases the permeability, or the mu value in the transformer, so that the magnetic fields are highly intensified, and so you can couple power from a primary to a secondary in a transformer, whether it's audio or AC power or whatever. An example, bear in mind that anytime you do this, anytime you have a device like a capacitor or an inductor or a transformer, that when you increase their value, the velocity of electromagnetic energy slows down. And we'll get into that in mathematical detail in a little bit, but it slows down as it travels through the device. For instance, it's if it's a receiver or any kind of a radio. Within a radio receiver, the signal slows down as it passes through a capacitor, a coil, or a tuned circuit. Because the physical dimensions are very small, the time delays are minimal, but you have to bear in mind that it does slow down when it's going through a capacitor or a coil. These properties are used in delay lines and phase shifting in certain equipment. Radar uses delay lines. A lot of things do that, and phase shifting is quite common. Well, when an electromagnetic field is propagating through space, the electric field is defined as the E field, and the magnetic field is defined as the H field. Now this goes back to Faraday and Maxwell times. And at the lowest level, or the tiniest submicroscopic level, they always have to be perpendicular to each other. Remember about Ersted's retarded student. He held the compass wrong, and that's how they discovered this effect. This is a simple monopole antenna, just sticking straight up in the air and above the ground. And you can see, by definition, what we've done is we say, well, the electric field is parallel to the antenna, and the magnetic field, or the H field, is perpendicular. So it's going off at an angle. Oh, thank you, sir. Yeah, the H field is perpendicular and the E field is parallel. But the important point is that they always have to be perpendicular to each other, regardless of how large or how small the situation is. Now, if I'd like to take a quantum viewpoint of this. Most things, well, you go back to Max Planck. I've got him in here somewhere. There he is. Max Planck was a brilliant man who, a little over 100 years ago, is the guy that came up with the original Planck constant. And Morey mentioned Planck length, there's Planck time, there's anything that's the smallest of anything is in Planck units. And the simplest description that I can come up with for defining a Planck thing, or the original Planck constant, our universe is not infinite in size, it's finite. And so somewhere out there is some limit. We think now it's something like a little over 13 billion light years. But then if you look the other direction, you look toward something, whatever the smallest it is, if it's infinitely small, then it doesn't exist, because by going to infinity, we have made it completely go out of existence. So there has to be some minimum size that something has to be to still be something. I hope that makes sense. That's a real simplistic explanation, but Albert Einstein conceived, once he and Planck were contemporaries, and once Planck came up with this, Einstein said, well, the smallest unit of electromagnetic radiation he thought should be defined as the photon, which is correct. So what I came up with in this thing is, and these terms are just made up by me. The top one is, of course, Einstein's photon. But if we could look at the permeability and the permittivity of space and put it into quantum size. In other words, it's not just a great big mass like a big jar of mayonnaise. It seems to have structure, and the permitons and the permeatons would have to be perpendicular to each other in order to propagate electromagnetic radiation. I don't know if this is right or not. It's just pure theory on my part. And a question, one of the first of several questions that I came up with, the first of many questions would be, would there or should there be a precise balance between the permitons and the permeatons, and would there be pairs of these quanta supporting the propagation of electromagnetic energy through space? One of the things that people have studied, they took those numbers that we showed previously in Henry's and Faraday's and calculated the impedance of space. And it calculates out just almost not quite 377 ohms, which is defined as a pure resistance as the electromagnetic energy propagates through space. But if you get into some substance, and we'll talk about this a little bit, where those are not, or there are different values from those of space, where we're into relative permittivity or permeability, everything changes. Next question. The big one, how does a photon propagate through this environment? By definition, we say that light has to have something out there. I'm inclined to think that these things define the ether to allow the propagation of electromagnetic radiation, all of it, light and microwaves and radio and all of it. And if we ask the question, how would a photon propagate through this quagmire? Would it hop from a permeaton to a permeton, repeating back and forth in this manner? In other words, is a photon going to just skip through in this, like Maxwell said, from one to the other, to mag to electrical and back to magnetic? And the one question that I had would be, how many photons, if this is all the case, how many photons would a single permaton or permuton hold? Would it be just one or an integral multiple? In other words, would a single, if we knew that we could quantize these things, if we had a permuton, would it only hold one photon or would it hold a number of photons? Big questions. And I have no idea about the answer. And because these are hard questions, a lot of people, I've spoken with a lot of people, they just simply avoid these, and they refer to epsilon and mu as constants. In fact, it's becoming more common. If you read in this on the internet, they call these things constants, and that's those values that I showed you previously, but they're not constant. They can expand and they can contract, and the value can change, and in a lot of materials here on Earth, it increases by large amounts. One simplistic explanation that I have, wave action on the ocean moves the energy extracted from the wind. The wind pushes the waves forward, but the water doesn't go. The waves move, the motion moves, the energy in the waves move forward, but the water basically stays the same. It may be in a kind of an oscillating ellipse in the same place, but it doesn't go. So this is another question that I have, is how do photons propagate through space? Remember Mike said I wasn't satisfied with the explanation of antennas. I'm still not. Well, I went through this Planck stuff here. There is one, I've talked to people about this possibility, and they're quite skeptical, and the reason being is a few years ago, there was some scientist, and he decided he would play a big joke on the scientific community. So he came up with a lot of math, which he claimed quantized gravity. Now, Einstein defined gravity with gravitons, and thought it had a speed limit as the same as light. But this scientist came up with all these impressive equations that were published, and a lot of people were fooled, and he had a big laugh, and a lot of people were embarrassed. As a consequence, they're very skeptical to get into something like this. Oops. There we go. I'm going the wrong way. This thing's left-handed for me. Pardon? I don't know the man's name. I read about it, and he came up with this stuff, and it was very impressive, and a lot of people bought it.
Was it Dr. Feynman?
I don't think so.
He tried to quantize gravity also.
Yeah, I think this is another person, and he just did it as it was a joke to him. Since we've talked about the ether here, and Morey spoke about it also, I'd like to take a quick look on the concept of ether and some possibilities. The idea that there is an ether is very logical in that there should be some kind of a medium throughout space to allow the propagation of light and electromagnetic radiation. Historically, it may have risen from the experiments into the propagation of sound waves. Back in the 19th century, scientists placed an electric bell inside a glass jar, and while it was ringing, pumped out the air with a vacuum pump. As the air was removed, the sound diminished, and when a hard vacuum was in the jar, the bell could not be heard at all. The logical conclusion was, and they were correct of course, was that the air molecules were vibrated by the bell to allow the sound to propagate, and without these atoms and molecules it couldn't travel. Now this may have led to the famous Michelson-Morley experiment to try to discover the ether. The problem is, when you compare these two, air molecules are physical matter, and the mu and epsilon are not. They are so intangible and abstruse that you can't compare them with the air and sound experiment. Because of this, and I found it interesting what Morey said about this other experiment, that he did appear to find it, and Michelson Morley gave up pretty quick. They failed. But we know that these two properties, the permittivity and permeability, go through all throughout the universe, and that's the way that light and electromagnetic radiation travel. Now, there's always this question. There's a speed limit. When you were kids in school, you had to learn that the speed of light is 186,000 miles per second, or if you're metric, it's 300 million meters per second. But it includes distance and time. And so the mu and the epsilon are quite interesting in that, and going clear back to Maxwell, he worked a deal kind of like this, and somehow or another they were able to measure or calculate or determine the permeability and permittivity of space, and he was able to take these figures and come up with a very close estimate of the velocity of light. He was a little on the low side, but when you consider his work was done in the 1860s and 70s for the most part, this was quite an accomplishment. And this led him to the prediction that light itself is electromagnetic. And even until he died, unfortunately at a young age of 48, a lot of people did not accept his concept of light. Only a few of his close friends could understand it. Nowadays we know that it's a fact. But this is a little equation here that says C is the velocity of light. And the equation says it's the reciprocal of the square root of the product of the permeability and permittivity. Now if we're into a vacuum or outer space, those would be those values that were on the show previously. And if you do the math there, you will come up with the velocity of light in meters or miles per second. And so the thing is, now we know, we have a good understanding of what determines the velocity of light. Jointly, these properties form a cosmic time constant within a vacuum, but within materials, they're variables. And so the figure that they give you for the speed of light, you have to understand it. It's either in vacuum or outer space. Now, within certain earthly matter or materials, we know that their values vary with a corresponding effect on the speed of electromagnetic radiation. We can slow it down a lot in certain materials. A classic example is the variation of epsilon in water, or the permittivity. What's known as light refraction is, and you know, when you poke a stick in a bucket of water and it looks like it's bent, what that is we call it refraction, but the reason for it is the speed of light in water slows down because the epsilon, the value, increases. And at longer wavelengths down in the radio range, and now we're talking about HF radio for the most part, the epsilon value increases to around 78 or 80, which reduces the velocity of light through, not light, but radio waves through water to about 1/9. The square root of 80 being almost 9, radio waves go through water at only about 1/9 the speed. Now, this permeability varies depending on the frequency. Time you're up to light frequency, in the 400 or 500 nanometer range, light travels at about 3/4 of the speed of light in space. And the radio frequency is about 11%, or 1/9. One thing that's kind of interesting to me is while the permittivity or the capacitance in the water changes, the permeability apparently doesn't have any effect. So if you calculated the impedance in there, instead of getting 377 ohms, you're going to get a much larger value of impedance. So what it says is water is electrical in this case in nature, but not magnetic. Now, an extreme case, and there it is, a picture of a black hole. An extreme case would ask what happens to these values in a black hole. We know that things like iron can increase the magnetic permeability, and water or tantalum compounds can increase the capacitance. So if you look at a black hole, the one thing we know, it's extremely condensed material. When you have extremely condensed material, I would assume, maybe not everybody would, but I would assume that both of these values would go up by huge amounts. And what that says is that the velocity of light and electromagnetic radiation would slow down going into there. So that may or may not be right, and I can't get an answer. I have a good friend who is a PhD astronomer, and he thinks about it, but he hasn't given me a conclusion yet. These are some definitions from Dr. Krause's book on radio antennas. Again, they're energy storage media. The permeability stores magnetic energy, and I better use this or John will get me. The permittivity stores electrical energy. And each is able to store static energy, and together they propagate electromagnetic energy at the speed of light, depending on their two values. And the speed of light in space and the speed of light in water and so forth is vastly different. Now, this is where we do a little bit of math. I'm going to do these one at a time. This is that thing we just looked at, which says the speed of light is determined by our two properties, mu and epsilon. Now, this is the famous equivalence equation of Einstein. You have energy on the left and mass on the right side of the equation, and the velocity of light stuck in there. Well, you don't know exactly what to do with this, and it's the velocity of light squared, and so do you use metric or you do miles or what? You could get vastly different numbers if you just simply did the straight across math. But if we substitute, recall this is C, and we substitute our little equation up there for C, now we get a different situation. And you see that that we're substituting that equation for C. So now it's mass times our little equation squared, and we can do one more math trick, and it's called simplification of the radical. We got rid of the square root and the square, so we're down to simply the mass times those two things, and we do one more simplification step, and we get there. So you can say that in this case, the energy is on one side and the mass and the storage is on the other side, but then we go one more, and this is the ultimate equation as far as I'm concerned. This is the same as Einstein's equation, except it takes out the velocity of light, and he probably wouldn't like that because velocity of light includes time. You say miles per second. The second is the unit of time. But it's conceivable that these properties here may have, as I said earlier, it's maybe a cosmic time constant. But what's important here is all of the mass is on one side of the equation, and this includes everything that has any form of mass. And back when neutrinos were first found, some people assumed that they were massless. In the long run, it turns out that they have a tiny, tiny, tiny amount of mass. And so it gives them a little inertia. So every atomic particle, quarks and protons and deuterons and all that stuff go here. And on this side is pure electromagnetic energy and the storage of it. So we can go back. I've got them in a sequence here, like like you're working equations on the blackboard in high school, and you work your way down, and you wind up with this same conclusion of this. So this equation right here is exactly the equivalent of Einstein's thing right there. And this is this little mathematic manipulation that I did. Let's step forward here. Oops, too far. As I said earlier, our entire universe is filled with these two properties, permeability and permittivity. And up to this point, we've been concerned only with the electromagnetic nature of space. It appears to be distributed throughout our universe, but what about outside? The size of our universe has been estimated to be about 13 billion light years across, if you can use the term across. I don't know, it's something that big. But if it is really finite in size, it must have a boundary out there somewhere. So if that curved line on the right is our outside boundary of our universe, it's going to be moving outward in that direction of the blue arrow. Oops, wrong button. It's going to be moving in that direction at extremely high speed, and the astronomers claim it is accelerating. So on the inside of the line, there are our old friends, these properties, the mu and the epsilon. They are uniformly distributed, and the values would be the same as those shown earlier, I think. But I asked Dr. Krauss one time, and he said, well, it's the same all through the universe. I said, how do we know that? Something that's 1 billion or 2 billion light years away? Well, that's just the way it is. So that's what he said. Outside the boundary, you'd say, well, this is true empty space, because, see, if you don't have mu and epsilon out there, light can't go through there. Radio waves can't go through there. Nothing electromagnetic, because without our two little friends here, they don't go. And so you could say, well, this is empty space, but by our definition, it's not really space. It's just totally nothing, absolute nothingness. Good theory anyway. This is true emptiness. Maybe it would be best described as empty nothingness. Now, there may be other kinds of space. That is space within space. Let's see if this works. I got one more thing here. We'll go back. Space within space. Electromagnetic radiation, including light, has this speed limit. There's a question is, why should we ever want to go faster than this limit? And the answer is, in one word, is for space travel. And here's a supposition. Suppose we invented a spaceship capable of travel at 50 times the velocity of light, 50 c. Obviously, we would want to communicate with it, but conventional radio would be useless because it only travels at the speed of light. You can't talk to that guy. You're going to have a new method of communications to talk with your spaceships if they can exceed the speed of light. We're going to have to invent super communications. And one of the things in this thing, I've got this question that says space within space. Whenever we get into other areas, for instance, zero point energy, a real simplistic definition of zero point energy is if we take a volume of space and remove all the particles from it, and that includes every kind of atomic particle there is, and then we chill it down to absolute zero, we find that there's still energy in that space, and that's the 0 point. We're at 0 on the temperature scale, and so this space is absolutely empty. But, okay, thank you. But our little friends here are still in that ZPE space. So that may be where it comes from. There are other things. Wormholes, I've been reading about wormholes and superstring theory lately, and I don't know how it fits in with all of this. One of the things is about, for instance, gravity. Einstein said, well, gravity must travel at the velocity of light because light is that's the speed limit of everything in the universe. But a lot of people don't think that anymore. First thing about gravity, it is not electromagnetic in nature. And my astronomer friend thinks it's instantaneous. In other words, there's no time lag. There's also this thing called quantum entanglement, if you've read about that. That is to say, if you have two atoms or molecules, and they are, and I don't even understand what the quantum entanglement is, but they are related somehow, and any distance apart, even up to a light year apart, when one has an action on it, the other one will have the identical action. And even greater distances than a light year. We just don't know all we think we know about all this stuff. I'm going to running low on time here, but lightning, I have a little company that we manufacture a lot of things that are related to antennas and towers and things like that. But we manufacture products that prevent lightning from striking towers. And so I've done a lot of study in atmospheric research and so forth. And one of the things that you cannot find an answer for is why does lightning zigzag as it travels through the atmosphere? But logic would tell you if you have this huge voltage and it can be 100 million volts or more, why doesn't it take the shortest path in a straight line? Why does it do all this zigzagging? And you can talk about air molecules and other things, but it's conceivable to me that the permeability and the permittivity of space through which this lightning is propagating get warped somehow. And that's what causes the irregular patterns. And they're going, these two bolts are just going in all directions. One of my opinions about weather forecasting, the meteorologists, they are all primarily into thermodynamics, heat. All our weather is a product of heat. Well, there's a very good book, and I don't think I wrote it here, but it's published by the University of Oklahoma called The Electrical Nature of Storms. Dr. McGuire is one of the authors. And at least they're looking into the electrical things. Every raindrop has a charge on it. Every snowflake has a charge on it. They call them, well, the reason they call it meteorology is because anything that falls out of the sky is a meteor. A raindrop is technically a meteor. They call it a hydrometeor. And so at any rate, I'm inclined to think that we could predict our weather much better if we got into electrodynamics. Final deal is I wanted to talk about politics and economy, unpleasant subjects as far as I'm concerned. And I think that some of what John was talking about at the break there has to do with politics and economy. People want to make money. They don't want you to come in and tamper. If they've got a real fat deal going, such as making billions of dollars selling oil and building automobiles and so forth, they don't want somebody to disrupt it. And so it's going to kind of be a barrier for all experimenters in trying to come up with clean energy. To change over from petroleum to some form of clean energy would really disrupt our economy right now. And there's too many powers in Washington, D.C. and all over the United States that are making huge amounts of money off that and that don't want to give it up. One thing I observed here, if someone from here at the conference last year would have told us that we would be paying over $3 a gallon for gasoline at this time this year, we'd say, well, you're nuts. Well, maybe it'd be $4 next year or $5. We don't know that. But at any rate, these quarterly returns from these oil companies are just astronomical, just the multiple billions of dollars. So anybody that gets into this alternative energy, clean energy, is bucking that. Both from the financial and the political both. They have enormous power. I'll tell a quick story about conspiracy that is an example for possibly this. Back in the first half of the 20th century, streetcar and interurban systems were built all over the United States. They were electric powered, so they were low pollution. And there is the classic example of Los Angeles. It was on CBS 60 Minutes one time. When the automotive manufacturers and the oil companies realized by the 1920s, people were buying millions of automobiles. I mean, there were Model Ts, but they were still automobiles. And so they recognized that there's huge amounts of money to be made building these vehicles and the fuel for them. And so they all got together and they formed corporations called National City Lines. And the one in California, the principal stockholders were General Motors, Standard Oil, and Firestone Tire, which is back then was married to Ford Motor Company. And what they did, the streetcar and interurban systems were privately owned. They were corporations. And that system had 1,100 miles of track all over the whole LA area. It was very efficient. You could go from downtown LA out to where the Disneyland is now in like 25 minutes. Today it's an hour and a half to 2 hours in bumper traffic. And so the question was on 60 Minutes, they said, what happened? Well, this corporation called National City Lines began to buy stock, and they bought more and more stock. And once they got a controlling interest, they said, no more maintenance, no more new equipment to replace the old worn-out equipment. We want to sell automobiles. And so as the system began to break down due to lack of maintenance and new vehicles, people couldn't rely on it anymore. So I got to get to work on time. I'll have to drive my car. Streetcar won't get me there. So what they did, they broke the system up. They abandoned a piece at a time, and it took them years to do it. When it was all done and destroyed, there was a trial. Oh, incidentally, they used the rights of way for the interurban lines is where a lot of their freeways are today. They wanted those interurban lines for freeways. And so there was a trial, and it was a conspiracy trial. And I believe it was in a federal court out there. And they found the corporation guilty of conspiring to destroy the public transportation system. And they fined the corporation $5,000, and each officer was fined $1. And the following year, General Motors sold $11 million worth of diesel buses into the LA area. So $11 million worth of buses plus the billions of dollars worth of vehicles and fuel since then. What my point about all this is, don't be surprised if you're bucking the system whenever you get into this. So the final thing is, we all just need to keep plugging away at this. And one of my favorite lines is old Winston Churchill used to say, never give up, just never give up. Thank you.
Okay, we have about 5 minutes for questions. If anybody has one for Ron, we'll take them in the usual manner from the stage left over here. Anybody have any questions?
I gave them all the answers already.
Thank you, Ron Nott. Appreciate it.
Or put them to sleep, one or the other.
Okay, we'll be back in about